Hi students, welcome to the session of electrodynamics. This chapter mostly deals with the idea of electricity and magnetism. Then what is this electricity and magnetism? The whole thing is designed for a graduate student here. So this chapter deals with most of the static charges and with the moving charges. So first of all, we'll deal with for a static charges and its basic law and its basic concepts. So first of all, we'll start the chapter electrostatistics. Electrostatics. You know, the electrostatics chapter deals with the static charges. If the charges are in motion, then in the lower classes you have learned about it may create some current, and according to that current there may create some magnetic field. So from this point onwards, we are only dealing with a group of charges or a single charge which is only steady. Okay. So first we'll go about the basic law, which is the Coulombs law. What Coulombs law will do is, this Coulombs law will give an idea of electric field. So first of all, consider a group of or a bunch of charges which are at rest. I name it as Q2, Q3, Q4, Q5, etc. So that another test charge which is at a distance r from any one of these charge will experience a force. How much force it will experience is given by this Coulombs law. So Coulombs law says that this force is directly proportional to product of one of the charge on the test charge, and force is directly proportional to 1 by r square, where r is the distance between these two charges. So you can club this equation, which is equal to F is proportional to Q by r square, which can be deal with a constant Q by r square. So F is equal to 1 by 4 pi epsilon 0 Q by r square. Since F is a vector, we should write 1 by 4 pi epsilon 0 Q by r square into r cap. So this is the equation for force acting by this charge Q on this test charge capital Q. So in the case of Coulombs law, F is inversely proportional to 1 by r square and F is directly proportional to the product of their charges. This is the definition of Coulombs law. So Coulombs law gives the idea of what is the force acting on that charge. So if there are n number of charges, the total force is equal to force acting by the first charge plus force acting by the second charge plus like that up to the force acting by the n charge on the test charge Q. So I can write like this, which is equal to 1 by 4 pi epsilon 0 Q1 Q by R1 square, where R1 is the distance from the first charge to the Q charge. R1 is the distance from the first charge to the test charge Q, and similarly I can write 1 by 4 pi epsilon 0 Q2 Q by modulus of R2 square plus 1 by 4 pi epsilon 0 Q3 Q by R3 square. Remember, we should put the unit vectors corresponding to each distance, R3 cap, like that. So one thing is common here, which is Q. So I can take 1 by 4 pi epsilon 0 Q1 by R1 modulus of R1 square into R1 cap plus Q2 by modulus of R2 square into R2 cap, etc. into Q. I name this quantity as a quantity which is equal to Q into this quantity, I name it as E, which is equal to force. So what is this E? What is this E? This E is called actually the electric field. This is called the electric field. So what is electric field? It is the force acting per unit charge on a test charge, which is equal to force acting on a test charge, So which is equal to, E have the expression 1 by 4 pi epsilon 0 q1 r1 square into r1 cap plus 1 by 4 pi epsilon 0 q2 by modulus of r2 square into r2 cap, etc. if there are a bunch of charges. So in general, I can write electric field as the equation E is equal to 1 by 4 pi epsilon 0 sigma I runs from 1 to n qi q by modulus of ri square into ri cap. This is the equation for electric field. What is actually really the electric field? Initially, Maxwell itself believed that electric field and magnetic field are some vibrations inside the, or vibration through the ether medium. But we know that the special theory of relativity removed that idea of ether medium, and I can't explain what is really a physical interpretation of electric field that you can think about it. So electric field we can give only in the term of force, which is equal to E is equal to F by Q. So its unit is Newton per Coulomb, where Coulomb is the unit of charge. So there are some laws corresponding to this electric field, which is we can write. So according to this electric field or the distribution of charges, things may vary. How the distribution of charges may vary. Suppose there is a line of charge, there is a surface, and there is an volume. How the charges can be distributed according to this line, according to this surface, and according to this volume. So we are dealing with continuous distribution of charges. You know that there are two types of distribution of charges. One is discrete distribution of charges and continuous distribution of charges. So continuous means along a line the charges will be continuous. You can't separate it as a q1 or q2. Instead we take it as dq, a small charge through a length dl. So there are three types of distribution of charges. One is linear distribution of charges, and surface distribution and volume distribution. For linear distribution, I am giving the name as lambda, and for the surface distribution, I am giving the name sigma, and for the volume distribution, we will give the name rho. So now we will look what is this lambda, sigma, and rho. Okay. So consider a line of charge in which I am considering a small length dl. What is the electric field at a point P from this element to this point P if this set a distance r? What is the electric field at this point P? For knowing the electric field, we want to know how much charge is there along this, or how much charge is there in this small element dl. So for this small element dl, we have a charge dq. Then electric field can be written as, from our equation, electric field is equal to 1 by 4 pi epsilon 0. Initially we have written as E is equal to 1 by 4 pi epsilon 0 sigma qi by modulus of ri square into ri cap. Now onwards I is equal to 1 to n, but these I are discrete values. Now it's a continuous value, so I can write it as dq by modulus of r square into r cap. So this is the electric field produced due to this small element dl, which contains dq amount of charge. So if the charge density, linear charge density is lambda, so what is density? Density, linear charge density is equal to dq by dl. How much charge is present in that small element? dl will give you the charge density lambda. So I can write dq as dq is equal to lambda into dl. So the electric field corresponding to this dq is equal to 1 by 4 pi epsilon 0. dq is lambda dl by modulus of r square into r cap. So the total electric field, there is a small problem here. This is due to the small charge dq. So I should name it as dE, which is a little bit of electric field produced due to this small dq. So the total electric field, I should integrate it as E is equal to integral dE, which is equal to 1 by 4 pi epsilon 0 integral lambda dl by modulus of r square into r cap. So on rewriting that equation, we have E is equal to 1 by 4 pi epsilon 0. What will be this? Lambda is a constant, so lambda will come here, and integral r cap by modulus of r square into dl. This is the equation for electric field produced due to an continuous line charge distribution. As a note, I will add one more point. As a note, initially we had talked about there is a small distribution of charges which have q1, q2, q3, etc., qn charges, and a test charge is placed at a distance. So I'll consider a xyz coordinate system in which this q1 and some of the charges, here the position vector is r1, and to the q the position vector is r1 dash, then the distance r, this is this distance vector r. So this vector, this r represents the distance from the source point to the field point. Q is at the field point, so from the source point to the field point is this distance r. Don't mix it with this distance r is from the center. It is, this r is not from the center, this r is from the source point to the field point. The whole paper deals like this. Always the r is from the source point to the field point. So similarly, this is the source point and this is the field point, so I named it as r. So whatever may be the charge distribution, that r will be a distance from the source point to the field point. Similarly, we look for an surface charge distribution. This is for a line charge distribution where lambda is called the linear charge density. Now we look for an surface charge density. So consider a surface which has lots of charges on its surface, and I am considering a small area dA here which consists of dq amount of charges. So the surface charge density sigma is equal to dq by dA. So E will become, E is equal to 1 by 4 pi epsilon 0, the small electric field at a point P due to this charge distribution is equal to 1 by 4 pi epsilon 0 integral, before integral we will write dq by r square into r cap. So which is equal to dE is equal to 1 by 4 pi epsilon 0 sigma dA by r square into r cap. I am substituting what is dq here, dq is equal to sigma dA. So d is equal to, so the total integral d is equal to 1 by 4 pi epsilon 0 integral sigma dA by r square into r cap. Since sigma is a constant, I can take it out. So the total electric field is equal to sigma into sigma by 4 pi epsilon 0 into 1 by r cap by r square into d. This is the electric field produced due to an surface charge distribution. Similarly, for a linear charge, for a volume charge distribution, consider a volume. It should not be in the shape of a cube. Consider sometimes in a volume like this. You can take any three-dimensional object. So if it's consider a volume d tau, and this contains dq amount of charges, so the volume charge distribution is equal to dq by d tau, where d tau is the small elementary volume. Just like the small elementary area, the electric field, similarly the equation for electric field will become rho by 4 pi epsilon 0 into integral r cap by r square d tau. This is the equation for the surface charge distribution. And one more equation we have, E is equal to 1 by 4 pi epsilon 0 lambda into integral r cap by r square into dl. This is the equation for linear charge distribution. This is the equation corresponding to linear charge, surface charge and the volume charge distribution. Now we will check how we will represent the electric field, diagrammatically or pictorial representation, or by the equation and the properties of electric field lines. The electric field lines represent how a charge is experienced, or how a charge experiences a force. The line along which a charge experiences a force will be represented by the electric field lines. And some of the properties of electric field lines are they never intersect. And they starts from the positive charge, and ends in negative charge. And through the surface, it is always perpendicular to the surface. These are the properties of an electric field line. So suppose you consider a sphere in which number of charges are there, some charges are there, which creates an electric field like this, a positive charge. The number of electric field lines passing through the surface of the sphere is equal to the electric field density. The electric field density, I name it as electric field density, is equal to n by 4 pi r square, where 4 pi r square is the surface area of the sphere. So n by 4 pi r square, in which the electric field density is directly proportional to 1 by r square. So basically, similarly, this has an idea of the modulus of the magnitude of electric field is also has the dependence of 1 by r square. Okay. So actually, this electric field density and magnitude of electric field both are similar. So we will check how to draw the electric field. Suppose there is a positive charge. In which the electric fields are emerging, or which told that the electric field starts from the positive charge and ends in the negative charge. So electric field I am drawing like this. I just draw this like this, electric field. And I am drawing some small vectors here. And another small. Why this small arrow marks? Why I am drawing this small arrow marks? Because E is a function of 1 by r square. E is directly proportional to 1 by r square. As distance increases, its intensity decreases. This is how we can show the electric field, but it is a better way is from a positive charge the electric fields are emerging. This is also a representation of electric field emerging from an positive charge. So if there is a negative charge, if there is a positive charge and a negative charge, how will we draw the electric field lines? The electric field lines will go like this. From positive charge, it will come to the negative charge like this, and like this. From the positive, you can see in your reference textbooks, the field lines will come to the negative charge, and that's how actually they are getting attracted. They are getting attracted like this. So this is the way in which we will represent the electric field lines. Now we are going for these are the introductions about the electrostatics and the corresponding electric field. Now we are going for a very important theory in electrostatics, or the law, not theory, it's a law corresponding to this chapter. First one is the Gauss's law. Gauss's law. So Gauss's law, the case of Gauss's law, we will go in a different approach, the simplest approach. Consider a sphere. Consider a sphere in which it has an charge at the center, a charge at the center of the sphere, and due to this charge, some of the electric fields are emerging out, and I am checking through a small area dA. The blackened one is dA, and this dA is always perpendicular. The area vector is always perpendicular to the surface. So at the point P, what is the electric field? What is the electric field? So we know that the electric field at any point is equal to 1 by 4 pi epsilon 0 q by r square, the magnitude of electric field. And this magnitude of electric field is nothing but the electric field density. We can compare that. So the electric field passing through this area is equal to the number of electric lines passing through, field lines passing through this area is equal to E into the small area dA, which is equal to 1 by 4 pi epsilon 0 q by r square. But this is an incomplete way of defining how much electric field is produced. Suppose you have an electric field going like this, and uniform electric field, and you have an area like this which has an area vector like this, and area is perpendicular to this surface like this, and the electric fields are going like this, and the angle is theta. Along the area vector, how much electric field is passing? That is actually the term electric flux, which is equal to the electric flux produced is equal to E dot dA. So along this, how much component of electric field will go, which is equal to E cos theta, which is equal to E dA cos theta. This is the electric flux through this small area dA. So similarly, through this small area, how much electric flux will be there, which is equal to, then this will give an idea of E dA, which is equal to 1 by 4 pi epsilon 0 q by r square. Actually, so that if there are another charge q2, this is q1, I name it as charge q1, q2, what is the electric flux through that surface? The electric flux through that surface will be equal to this is the, now while this q becomes q1, this becomes the electric field due to this first charge. Now what will happen if I am measuring the electric field due to the q2 charge? E2 into through the small same area will be equal to 1 by 4 pi epsilon 0 q2 by r square. Similarly, the total flux will be then equal to phi1 plus phi2. If there are n number of charges, the total flux will be equal to phi n. So I am giving the term letter phi for the electric flux. These are all the school level topics. That's why we are going little bit faster in the terms of flux itself. So phi is equal to, what is phi? 1 by 4 pi epsilon 0 q1 by r square into dA. this is phi 1 into dA will give you the phi 1, and which is equal to plus 1 by 4 pi epsilon 0 q2 by r square into dA, like that it will go. So the total flux I can write it as, if it is a continuous distribution of charges, I can write 1 by 4 pi epsilon 0 total charge, which is the q1 plus q2 plus q3, which I am writing it as q enclosed by r square into dA. Q enclosed into d. This is the flux produced through an sphere. So we know that this r it's an constant, so I can write it as phi is equal to 1 by 4 pi epsilon 0 q enclosed by r square into integral dA on integration of this small area. If you integrate using the spherical coordinate system, where dA is equal to r square sin theta d theta d phi, this you have learned in mathematics, which is equal to r square sin theta d phi. On integration dA, you have to apply 3 integrals, where if r is a constant, then r square will come out. You have 2 integral from 0 to pi sin theta d theta, and from 0 to 2 pi d phi. So on integration you will get, if you try, you will get it as 4 pi r square, and this pi and pi will go, 4 and 4 will go, r square and r square will go, and the remaining thing is epsilon 0 and q enclosed. So the total flux through the surface is equal to q enclosed by epsilon 0. So what is the criteria? This surface is a closed surface, because this total surface is a closed surface. So we should write Gauss's law as, along a closed surface, closed integral E dot dA, the total flux is equal to the total charge enclosed by epsilon 0. This is the definition of Gauss's law. So Gauss's law states that the total flux through any closed surface is directly proportional to the total charge enclosed through that surface, or the total charge enclosed in that surface. And what are the main speciality of Gauss's law is, you can take, the surface should be a closed surface, you can take any 3-dimensional surface to represent or to explain the electric field at any point using this Gauss's law. But if you take any arbitrary shape, I can't say whether the electric field will be exactly perpendicular or exactly parallel with the area vector. So that depends, and anyway these are the main idea of Gauss's law, and we have to learn some of the applications of Gauss's law. And now we have to write, this is an integral form, now we want to write the Gauss's law in a differential form. So how will we write that Gauss's law in a differential form is the next question. So for that, let us rub off this, and now we'll write Gauss's law. So according to Gauss's law, closed integral E dot ds is equal to q enclosed by epsilon 0. So just write and make it in a box. This is a very important law, not ds, we have to take the term dA, where A is the area vector. Now consider a surface which has a small volume distribution d tau, and its surface charge density, the volume charge density is rho. What is the electric field produced at a point P by this surface charge distribution? I told you, you can easily find out what is the electric field at the point P using Gauss's law. So what we will do is we will take the total charge enclosed. Sometimes we can't find what is the total charge enclosed for an arbitrary shaped body. So what we will do is, this q enclosed will be measured in terms of, you know that the total charge is equal to the surface charge, the volume charge density into its volume. So we have a small volume d2, so I should write the Q enclosed is equal to integral rho d2. So I am substituting this Q enclosed to this closed integral E dot dA to the equation of Gauss's law. So closed integral E dot dA is equal to integral rho d2 by epsilon 0. Now there arises a problem. Here it is an area integral and surface integral, and here it is a volume integral. So how will you solve this? So this you have learned in Gauss's divergence theorem. Again, it's a mathematical rule that you are learning in mathematics. So apply the Gauss's divergence theorem. So do you remember what is the Gauss's divergence theorem? This Gauss's divergence theorem says that closed integral or the surface integral A dot dA, if area is any vector dA, can be written as divergence of A through that volume d2. So I can rewrite this closed integral E dot dA in terms of its divergence. So writing integral del dot E d2 will give you integral 1 by epsilon 0 times integral rho d2. This is true for all volumes. We can take out the volume integral and I can write del dot E is equal to rho by epsilon 0, where rho is called the volume charge density. This is the differential form of Gauss's law, where rho is the total or the volume charge density, and rho del, you know that del is equal to dou by dou x of I plus dou by dou y of j plus dou by dou z of, sorry, I'll write, it's the better way to write, it is j plus k cap into dou by dou z. It's an del differential operator. This is the Gauss's law in differential form. Now we will look about what are the applications of Gauss's law and how Gauss's law calculates for an arbitrary shaped body, for example the sphere, the cylinder, and for some other things like shell or a plain sheet of charged sheet. How will we calculate the electric field at different points? That we can now check after writing all those things, and this is the basic idea, but for deriving the equations you can use both the equations. The better way is use the integral form of Gauss's law. Now we will discuss about the extraordinary powers of Gauss's law. So just like saying there are some extraordinary powers for this Gauss's law, just like the main extraordinary power what I called was rho should not be, need not to be uniform. Gauss's law works for if the volume charge density is non-uniform distribution. So we will check about what are the applications of Gauss's law. Applications of Gauss's law. First of all, we will consider a sphere, a uniformly charged sphere. Consider a sphere of radius r. Consider a sphere of radius r in which it is uniformly distributed to a charge density rho. Uniformly distributed charge density rho. Now I should find out at a point P what at a and from a distance r from the center of the sphere, what is the electric field produced. This is at the point P. For that I am considering a Gaussian sphere which is represented as a dotted line, and at this through this Gaussian surface or the Gaussian sphere, what is the electric field produced at this point, which is equal to in this direction, and this area vector is in this direction. Now we'll write the basic Gauss's law. The Gauss's law is closed integral E dot ds is equal to q enclosed by epsilon 0. What is q enclosed actually? The q enclosed, the total charge enclosed, is equal to rho into or integral rho d tau, which is equal to rho into integral d tau, integral d tau, which is equal to rho into 4 by 3 pi r cube. 4 by 3 pi r cube, where r is the radius of the sphere. Now I am going to substitute. Sorry, we are using always dA. ds is also a representation of surface area, but initially we took dA. So we'll go for the whole chapter, we will take it as dA. So closed integral E dot dA, which is equal to rho by epsilon 0 into 4 by 3 pi r cube. Just look what is E dot dA. E dot dA, the angle is 0 degree, so which is equal to EDA cos 0 degree, which is equal to EDA. So I am substituting EDA in closed integral EDA is equal to rho by epsilon 0 into 4 by 3 pi r cube. So we want to find out what is E. E is equal to integral dA, which is equal to the same thing. What is integral dA? Integral dA is with this Gaussian surface, which has the Gaussian sphere, which has the radius r, which is equal to E into 4 pi r square, which is equal to rho into 4 pi r cube by 3 epsilon 0. 4 pi and 4 pi will go. So E is equal to rho r cube by 3 epsilon 0 r square. This is the electric field produced at the point outside. So since a vector, I should write a unit vector r cap along this direction, which is the electric field produced at an outside point P for a uniformly charged sphere. Similarly, I will look for electric field at the surface. Same process, but we should consider where is this Gaussian surface. Gaussian surface is exactly on the surface of the sphere, which is this r, and now the area integral dA will become 4 pi r square. So I can write it as Gauss's law, closed integral E dot ds is equal to closed by epsilon 0, same thing, or taking in a simple step you can take r is equal to r, but as a process I will show how this will become r is equal to r. So which is equal to closed integral E dot dA is equal to q enclosed by epsilon 0. So E into 4 pi r square is equal to q enclosed rho into 4 by 3 pi r cube. So we will get the equation as rho by epsilon 0. So I forgot to put that epsilon 0, which is equal to 4 pi and 4 pi will go, which is equal to r square and r will go, which is equal to rho by 3 epsilon 0 r. Along the, if you are taking along this point, this is also radius, and I can name it as r cap, which is along the r cap direction, along that radius, unit vector along that radius. So which is equal to E at the surface. This is the electric field produced at the surface of the sphere, and mostly this is a constant, because r is a constant, all these quantities are constant. So now we will look what is the electric field produced at the, or produced inside the sphere. Electric field produced inside the sphere. So we will write from the beginning or it's a new diagram. This is the sphere of radius r, and through this point inside the sphere we are taking a small radius r1, at which I am considering a Gaussian sphere inside the sphere. Now this is the point where I want to find out how much Q is enclosed through volume. So which is the Q enclosed? What is the Q enclosed? So Gauss's law says that closed integral E dot ds dA is equal to Q enclosed by epsilon 0. So I should find out what is Q enclosed. Since it is a uniformly charged sphere, I can write Q enclosed is always, or the enclosed charges, I name it as Q dash. Q dash is due to, or Q1, which is due to this inside space. So I can write Q1 is equal to rho into volume corresponding to that sphere. The how much charge is enclosed, which is equal to rho into volume is 4 by 3 pi r1 cube. But we know that what is the total charge enclosed? Total charge enclosed is equal to Q. I name it as, which is equal to Q is equal to rho into 4 by 3 pi r cube. 4 by 3 pi r cube. So I can write it as Q1 by Q is equal to, dividing these two, equation 1 and 2, I will get it as rho and rho will go, 4 by 3 will go, which is equal to r1 cube by r cube. So Q1 is equal to r1 cube by r cube into Q. R1 cube by r cube. So now we will apply this Gauss's law, which is equal to integral E dA is equal to r1 cube Q divided by r cube into 1 by epsilon 0. 1 by epsilon 0. So what is dA? dA is equal to 4 pi r1 square. Now I should consider the surface area of this sphere with r1. So which is equal to 1 by epsilon 0 into r1 cube Q by r cube. So which is equal to, this small letter q is the total charge enclosed within the sphere, which is equal to 4 r square will go, and we will go get it as 1 by 4 pi epsilon 0 Q r by r cube. Q r by r cube. So this is how we can write the Gauss's electric field outside the sphere, which is in the r1 cap. So electric field inside the sphere is equal to 1 by 4 pi epsilon 0 Q into r1 by r cube into r1 cap, where E is now proportional to r1, and here E is a constant, and outside the sphere, you remember E outside the sphere is directly proportional to 1 by r square. 1 by r square. Now we will draw a graph to show how the electric field is varying for a uniformly charged sphere. For that, consider a sphere and an electric field in y-axis, taking electric field in the y-axis and distance along r along the x-axis. Now till the surface, electric field is varying inside the sphere. This is inside, this is at the surface. Till the surface, electric field is directly proportional to r, and it reaches its maximum at the surface, and again varying as 1 by E is proportional to 1 by r square. This is the variation of electric field inside and at the surface, and at this point r is equal to r, and E is proportional to 1 by r square. This is how electric field is varying inside, at the surface, and outside the uniformly charged sphere. Now we will look for a uniformly charged cylinder. What will be the case? For a uniformly charged cylinder, we will consider the spherical. We should not consider the spherical symmetry, we should consider the cylindrical symmetry. So, for a uniformly charged cylinder, for that consider a cylinder of radius r, its radius is r, and I want to find out outside the cylinder, electric field outside the cylinder, on the surface of the cylinder, and inside the cylinder. The same process, consider a Gaussian cylinder, at the point P, where we want to find out the electric field, in which the cylinder, now the cylinder has a length L. Now, what is the electric field at this point P? For that, we are considering three different surfaces, two base and one curved surface. So, I will write the Gauss's law, closed integral E dot ds is equal to integral 2 into the upper surfaces or the base surfaces 1 and 2 E dA plus E dot dA plus integral through the curved surface E dot dA, So, what is the angle between electric field is in this direction and area vector on this base surface is in this direction actually. So, what is the angle between this area vector and electric field? Through the base surfaces, E dot dA is equal to 0 because angle is 90 degree. So, closed integral E dot dA will now changes to the curved surface EDA, which is equal to Q enclosed by epsilon 0. So, same process, the Q enclosed is equal to integral rho d tau, which is equal to rho into integral d tau, what is the total volume of the cylinder, which is equal to pi r square L. So, Q enclosed is equal to rho pi r square L. So, substitute here, which is equal to E into integral dA is equal to rho into pi r square L. What is at this point P, which is at a distance r, so which is equal to E is equal to 2 pi r L is equal to rho into pi r square L. So, which is equal to pi and pi will go, this L and L will go. So, electric field is equal to rho r square by 2 r into r cap. This is the electric field produced outside the cylinder. Now, at the surface, what is the electric field produced? Simplest idea is put r is equal to capital R, because this we are considering this Gaussian, we will consider this Gaussian surface on the surface of the cylinder itself. So, r is equal to r, that will give you integral EDA is equal to rho into pi r square L, which is equal to E into 2 pi r L is equal to rho into pi r square L. So E is equal to pi and pi will go, which is equal to L and L will go, which is equal to rho r by 2 epsilon 0. 1 epsilon 0 is there. So rho r by 2 epsilon 0. This is the electric field produced, or the electric field at surface of the cylinder. Now we will check what is the electric field produced inside the cylinder. For same process, there is not that much difference. Consider a cylinder with radius capital R and its length is L. Now consider a point inside the cylinder with radius R. This is at the point. So integral E curved surface EDA is equal to Q enclosed by epsilon 0, which is equal to E into, now the area is 2 pi R L is equal to Q enclosed is equal to rho into pi R square L by epsilon 0. Pi and pi will go. So E is equal to rho into R by 2 epsilon 0. Since pi and pi will go, 2 will come down and L will be cancelled. So one R will be remaining. So E is directly proportional to R. So E at the surface is a constant. E outside the sphere is equal to E out is directly proportional to 1 by R. Now how will we draw this graph? We will consider a cylinder of radius R in which E is directly proportional to R, and the surface it will reach the maximum, and again it will come down as function of 1 by R. E is directly proportional to 1 by R. This is the graphical representation of how electric field varies outside at the surface and inside cylinder. So this is the case for an uniformly charged cylinder. Now we will check how the electric field is varying for a uniformly charged shell. For a charged shell means a hollow sphere with a radius R. Shell is with a radius R. Now the charge, we are giving some charge and it will reside, positive charge, it will reside only on the surface of the shell. It will reside only on the surface of the shell. Now writing the Gauss's law, closed integral E dot dA is equal to Q enclosed by epsilon 0. Here the Q enclosed, or outside the point, we want to find out outside, surface and inside, the same process, but some difference, that we want to find out what is the total electric field produced at the point P. So for that, consider a Gaussian surface of radius R. So E into its surface area 4 pi R square, which is equal to Q enclosed is sigma into 4 pi R square. Why sigma into 4 pi R square? On the shell, the charges will reside only on the surface. So the Q enclosed is equal to sigma into 4 pi R square. I am substituting that value, which is equal to sigma into 4 pi R square by epsilon 0. So therefore E is equal to 4 pi and 4 pi will go, which is equal to sigma R square by R square into epsilon 0 into R cap. This is the electric field produced outside at a point outside the shell, which is a function of E is directly proportional to 1 by R square. This is the total charge enclosed through this Gaussian surface. Now, what is electric field at the surface of the shell? At the surface of the shell, put R is equal to R. So what we will get is E out at the surface to sigma into R square divided by R square into epsilon 0 into R cap. So which is equal to sigma by epsilon 0, which is a constant. So this is the electric field produced at the surface of the shell, which is in the direction of the radius vector, unit vector, which is equal to R cap. And the most interesting idea is what is the electric field inside the shell. The electric field inside the shell, for that consider a shell and the whole positive charges are residing on the surface of the shell, and I am considering a Gaussian surface which is at a distance r, or which is at a radius r inside the shell. So what is the total charge enclosed inside this surface? The total charge enclosed is equal to 0. So the electric field inside the inside the shell is equal to 0. Electric field inside the shell is equal to 0. So I can draw a graphical representation of this variation of electric field with the distance r, which is equal to E, and this y-axis is electric field, which is same for the cylinder or the our sphere, and till inside the shell electric field is 0, then again it becomes a constant, then it varies according to 1 by R square is at the outside the shell. So till the inside the shell electric field is 0. This is the graphical representation of variation of electric field with distance for an uniformly charged shell. This is for an uniformly charged shell. These are the three cases we can talk about in the case of Gauss's law. But one more thing is there. If we have a charged sheet, uniformly charged sheet, in this case I am considering only an uniformly charged distribution. Maybe in the next lecture we will consider the non-uniform cases, just like the non-uniformly charged sphere. What is the electric field at a point, how the electric field will vary according to this distance if we consider a non-uniformly charged distribution. Now at last we will look for an charged sheet, a sheet of charge in which we have a uniformly charged sheet, and we want to find out what is the electric field produced at a point P up and down the charged sheet, which is at a distance something at some distance. So for that I am considering a pillbox, Gaussian pillbox, which has just like similar to a small matchbox, which has some surface area. Gaussian pillbox, which encloses the whole sheet inside that, which has a surface area A. So I am taking the electric field is in this direction, electric field is in this direction. So for this we know that this area vector is in this direction, and this area, the upper part area is in the direction of electric field, and lower portion also area vector is in the same direction of electric field. All other surfaces area vector is exactly perpendicular with the electric field. So I can write according to Gauss's law, closed integral E dot ds. What is this closed integral? How the edges, the total edge surfaces into E dot dA plus upper surface into E dot dA plus lower surface into E dot dA. So which is equal to edge surfaces E dot dA on the edge surfaces E dot dA become 0 because E and dA vector are perpendicular to each other. So the angle is equal to theta is equal to 90 degree. Now what about the upper surfaces and the lower surface? Now we will check E integral E dot dA plus integral upper surface plus integral lower surface dot E dot dA is equal to Q enclosed by epsilon 0. If the sheet has an area A, surface area A, and its surface charge density is sigma, then Q enclosed is equal to, what is Q enclosed? Sigma into A. The total charge enclosed is equal to surface charge density into the surface area. Similarly, E into integral dA plus E into integral is equal to sigma A by epsilon 0. So 2 into E A is equal to sigma A by epsilon 0. A and A will go. So the electric field is equal to 2 sigma by 2 epsilon 0 into n cap. This is the electric field produced at a point P up on the at a surface above the or below the charged plane sheet. For example, we will consider a charged sheet which has an positive surface charge density and a negative charge density. The better example which has the positive charges are here. All over the positive charges will be there. On this side also positive charges will be there. And similarly, this for a negative charges, and here also this negative charges. How will we draw this electric field vector? Now I will represent with negative charges. I will represent the blue color. The electric lines, field lines, I will represent with blue color, and for the positive charge it will be in the black color. So the blue for the positive charge, the electric field will be going in this direction. Electric fields of this positively charged sphere, and for a negatively charged sheet, not sphere, for a sheet, the field lines will come into the sheet. So what is the total electric field at this region 1, region 2 and region 3? The total electric field here it is 0 because this 2 will cancel out. Now here this will be E is equal to sigma by 2 epsilon 0 plus sigma by 2 epsilon 0, which is equal to sigma by epsilon 0, which is also 0. This is the electric field in between one positively charged and negatively charged plate. I hope you got the idea of how will you calculate the electric field at different points using Gauss's law. In the next lecture, we will be talking about work done in moving a charge and its electric potential. Before that, we want to discuss what for a non-uniform charge distribution, how will you apply this Gauss's law. Hope you have enjoyed my lecture, and thanks for hearing my lecture.